Hello once again. Again, I don't know if it's morning for you or afternoon for you or evening for you, but whichever the case may be, I hope you're doing well. We're going to continue looking at computational strategies for the arithmetic principle called subtraction. And you recall in the last segment, we got down to talking about combination pairs and compatible pairs and subitizing. I'm going to sort of skip over mental math because mental math, again, is one of those things where based on your understanding of the arithmetic principle called subtraction and your understanding of place value and your understanding of Piaget's conservation of number, that mental math is just taking an arithmetic problem such as subtraction and just modifying it in such a way to facilitate the arithmetic, but do it in your head. So you can't be using large or huge numbers to do this. But I think asking our kids to practice doing things in their head, mental math, I think is a good exercise because it helps them to depend on the idea of place value, depend on the meaning or the understanding of what the subtraction principle is. So I think mental math is important. But what I want to do is move on to value expanded form, place value expanded form as strategies for performing the subtraction. And in some sense, the value expanded form and the place value expanded form are somewhat the ideas of borrowing, except you're doing it in a very understandable, recognizable form or fashion. You're not doing it with some hocus pocus, putting numbers up above other numbers and trying to figure out what you're supposed to do. And so having said that, let's see what it is that I'm talking about. So let me go get Smartboard up, get me a full screen view. And so let's sort of make up some problems. And I'm going to intentionally make these where when I look at the menu in, and let's make it something like 242. And I want to subtract, let's say, 168. And I want to know what the difference is. I want to know if I have a box of 342 ball bearings and I remove 168 of those ball bearings, then how many ball bearings do I have left? Well, again, we've talked about strategies like shifting and some of the others, but what I'm going to do is take 342, 168, and I'm going to write those two numbers down in their value expanded form. So let's do that. So it's 300 plus 40 plus 2. And underneath that, I'm going to take the 168 and I'm going to decompose it or partition it according to place value into 100 plus 60 plus 8. And I want to perform the subtraction. Now, the one thing about subtraction, I want to be able to take the 168 from the 342, but I want to do it in such a way that, one, it makes sense to me, and I can do the calculations fairly easily. So here's what I'm going to do. Obviously, I can subtract 100 from 300. That's not a difficult problem. The two problems lie in the tens column and in the ones column, because it's not easy to subtract 60 from 40. Banks do it all the time, and you do it all the time, but in terms of calculations, I can't subtract 60 from 40, and I don't want to subtract 8 from 2. So what I'm going to do is I'm going to modify this problem so that I can perform the subtraction on them. And here's what I'm going to do. I want to make this number 40 big enough so that I can subtract 60 from it. And so I'm going to go next door to the 300, and I'm going to borrow. Now, in the classical borrowing procedure or the classical borrowing algorithm, they teach us to go next door and not just borrow what we need, which in this case, all I need is 20, because I can subtract 60 from 60. So instead of going next door to borrow a cup of sugar, they insist that you go next door and borrow a 5-pound bag of sugar, which you don't need. But I'm going to do that. I'm going to go ahead and borrow a little bit more than I need. But do you understand that really all I need is 20 to borrow from this one right here to facilitate the subtraction of 60 from the top number? I just need 20 more to make it so that I can subtract 60 from 60. Same way is true for the 8 from the 2. all I need is 6 more. I don't need to go next door and borrow 10 from that. I just need to go next door and borrow 6 so I can subtract 8 from 8. However, traditionally, here's what we do. I'm going to go next door and I'm going to borrow 10. So I'll go through this. That leaves me with 30. And when I move the 10 over here, adding 10 to 2 gives me 12. So I've modified the number in that column. Now I can subtract 8 from 12, and I'm okay with that. I'm still got a problem where I'm not trying to take 60 from 40, which was bad enough. I'm taking 60 from an even smaller number. So once again, I'm going to go next door to the 300, and I'm going to go over there, and I could only borrow 30 and change this down to 270. Okay, I could do that. But let me go through it. Let me write this as 200. Put 100 over here. So if I put 100 with the 30, it becomes 130. And now I've got all the numbers on top equal to or bigger than the numbers on bottom. And so I can subtract 100 from 200 and get 100. I can subtract 60 for 130. Now remember, this is power 10 arithmetic. The kids have already learned that 13 minus 6 is 7. So 130 minus 60 is 70. And they know I can subtract 8 from 12. Or if they don't like that, they can shift everything up by 2 and change the 8 into a friendly number and make this 14 minus 10, which is 4. And so maybe they are more comfortable with making that 14 minus 10 to get 4. But 12 minus 8 is 4. And then the last thing, all we need to do is write that in standard form, which is 174. And that's the value expanded form. And it's the closest of all the strategies that I will look at in terms of subtraction that come closest to the standard idea behind borrowing. So I'm going to do one more problem in which we are essentially borrowing, but we're borrowing in such a way that the kids, when they see what's going on, they see exactly what they're doing. There's no hocus pocus going on here. So let me look at a different problem. Let me choose 1053. Let me subtract 600. And I'm picking these numbers once again so that they are the digits of the subtrahend in some places, in some place value positions, are larger than the corresponding positions in the minuend. So I've intentionally made the subtrahend 679, which has 2 digits that are greater than the corresponding 2 digits in the minuend. So the 7 is bigger than the 5 and the 9 is bigger than the 3. So somehow I'm going to eventually have to rearrange my work so that I can take advantage of what? Single digit arithmetic, friendly numbers, and power 10 arithmetic. So once again, write this in value expanded form. So this is 1,000. There are no 100s. There's a 50, and there's a 3, and I'm subtracting 600 plus 70 plus 9. So this is my problem. Again, there's 1,000 here. I'm not taking anything away from it. And the hundreds column, I've got no 100s in the minuend, and I've got 6 100s in the subtrahend. So there's one of my problems. I can't take 600 from 0. And in the tens column, I can't take 70 from 50. And in the ones column, I can't take 9 from 3. So I'm going to go through the process of moving some numbers around to make it so that I can subtract parts of the subtrahend from parts of the minuend. So I'm going to start over on the right-hand side, and I'm going to change the 3 by taking 10 from the tens column. And so the 3 now is 3 plus 10. And I'm going to go ahead and write it as 13 because I've changed it by adding 10 to it. So subtracting 9 from 13 is okay. I can't subtract 70 from 40, so I'm going to go next door to get some more. Well, there's nothing sitting there, so I even have to go further down the block, to the 1,000. So I'm going to go down there and I'm going to borrow. Now, to subtract 600 from this number here, 0, I need 600. So I'm going to get 600. I'm going to borrow 600 to get the 600 that I need for this subtraction. But since I need some to give to the 40, I'm going to go ahead and borrow 100 more. So I've essentially borrowed 700. So this is leaving me with 300. Let me get the subtraction thing out of the way. So what I did is I went over here and borrowed the 600 that I needed for the hundreds column and 100 more that I need to fix up the tens column. So now I'm going to take this 100 and put it over here and make this 140. Now I've got all the values and the corresponding place value positions of thousands, hundreds, tens, ones, and I made it so those numbers in the minuend are as big or bigger than the numbers that are in the subtrahend. So now we can go and we can subtract. And by the way, I don't have to subtract right to left, left to right. Let's see, I'm not taking anything from the 300. 600 from 600 is 0. 70 from 140 is 70, or 14 minus 7 is 7, but it's tens, so it's 70. And then 13 minus 9 is 14 minus 10, which is 4. Now it's just a matter of writing this number in standard form. So it's 300 plus 70 plus 4, so it's 374. And that's the difference between 1,053 and 679. Again, I could solve this problem by using shifting, but right now I'm using value expanded form. So I've illustrated value expanded form. I'm not going to take the time to illustrate place value expanded form, because the ideas are still the same. It's just that you're writing the numbers in place value expanded form rather than value expanded form. And what I did here for value expanded form is exactly what you do in place value expanded form. So the next strategy I want to turn to is the one that I call minuend splitting minuend decomposition is probably better. It's just that I got used to calling it minuend splitting, and so it's hard to leave a term that I've started 3 years ago. So here's the idea in minuend splitting. So we've talked about shifting, we've talked about the value expanded form, and in minuend splitting, what I'm going to do is modify the minuend so that it becomes friendly with respect to the subtrahend. And so let me indicate what I mean by that. Let's take number 73. Let me subtract 48 from it. So I have a set of objects, 73. Could be 73 baseball cards. I remove 48 to give to my friend Jack, and now I ask how many baseball cards do I have left? Or I've got a box of 73 cookies. I take 48 cookies out of it to share with my third grade elementary class. How many cookies do I have left? Now, actually I could do this one by shifting, because I could take that subtrahend and add 2 to it to make it 50. And that would be a nice way to do this problem. So I could add 2 to make this 75 minus 50, and 25 is the difference. But that's shifting, and I want to talk about minuend splitting. And here's the idea behind minuend splitting. What I want to do is I want to take the 73, and I want to split it into 2 parts, where one of the parts is very friendly with respect to taking 48 away from it. Remember in subtraction, if I have a minuend set and I want to reach in and pull out a subtrahend set, the objects that I am taking out, I can pull out from anywhere in the minuend set. No one's telling me where to take, in this case, the 48 objects from. I just know that there's 73 objects, and I get to pick how I take those 48 objects out of there. So here's what I do. I'm going to take 73, and I'm going to split it into two parts. And what I'm going to do is I'm first going to take 3 away from it, and then I'm going to take one more, and you'll see why in just a moment. I'm going to take 3 away from it first. That'll make it 70, but I'm going to take 4 away from it. So I'm going to split the 73 up into 69 plus 4. Now, why would I choose to take the 73 and separate it into two parts? One, which is just under the friendly number 70, and a 4. Why would I do that? Well, remember, all I've done is represented 73 in a different way, which Piaget's conservation number says I can do. I wrote it as 69 plus 4. But now I can subtract the 48, and I'm going to choose to subtract the 48 from the 69 because the 69 has digits that are greater than or equal to the digits in the subtrahend. So it's easy. 4 from 6 or 40 from 60 is 20. And 8 from 9 is 1. And so I know that difference is 21. But the 4 I didn't do anything with. I didn't take anything away from it. So I've got to put that 4 back in. So the difference is 25. And that's the result we got when we used the strategy called shifting. 75 minus 50 is 25. The idea of taking the minuend and splitting into two parts or two pieces where one part or one piece is very friendly with respect to the subtrahend, that's a very good idea. And that idea works no matter what size numbers you have. So let's change the size of numbers and let's see what George is talking about. So let me create a new screen. Now again, we're talking about minuend splitting or minuend decomposition. Again, let me pick 841. Let me subtract 376. Once again, I intentionally picked the digits in the subtrahend, at least in two places, to be larger than the digits in its corresponding place value position in the minuend. I can't do that in the hundreds column, because if I get it in the hundreds column, then I've got a subtrahend that's too big. I can't take it away from the minuend. But in this problem, I've got 841. I want to subtract 376, and I want to avoid borrowing. So again, since I get to select or choose how I'm going to take the 376 objects away from the 841 objects, I'm going to go up here and I'm going to peel off 41. I'm going to peel off 41, and then I'm going to peel off one more. Once again, you're going to see what I'm doing is creating a number. Let's see, I took off 41 and I peeled off one more. That makes it a 42. Now I'm ready to subtract 376. Now, if I split 841 into 799 plus 42, why does that make this problem easier than the one I started with? Well, when I split off the 41 and then very carefully, judiciously chose to pick one more to get to 42, that creates a lot of 9s. And 9s are good as long as they belong to the minuend, not the subtrahend. So I put some 9s in the minuend, and so now I have to subtract 376 from the 799, and it's easy. This is a 4, this is a 2, this is a 3. I didn't do anything with the 42, so I've got to make sure I remember to put it back in. So now I have 423 plus 42. Well, here's 20 and 40, that's 60, and 3 and 2 is 5. So it's 465. And that's the difference. So I'm finding the difference of 841 minus 376 by not dealing with the original problem, but by modifying it so as to take advantage of friendly numbers. Now in this case, 799 is a friendly number, not in the sense that it ends in 0 or it ends in 5, but it's a friendly number with respect to 376 because it has bunches of 9s in it. And those are always friendly with respect to subtraction as long as those 9s belong to the minuend. Let's try another example. Again, this is minuend splitting or minuend decomposition. Let's take a bigger number like 4,175. Let me subtract 1,287. And the question is how different is that? I could use shifting on this by just shifting things up to the left or to the right to make sure that this second number called the subtrahend is a friendly number. But I'm going to choose, in this case, I'm going to choose minuend splitting. And so what I'm going to do is I want to subtract 1,287 from 4,175. Once again, I have three places where I've got some problems. The ones place, the tens place, and the hundreds place. So what I'm going to do is take this number, 4,175. I'm going to immediately remove 175, but I'm going to remove one more. So I'm going to take this number, and I'm going to remove 175, except I'm going to remove one more, so I'm going to remove 176. And that means the number that's left is not 4,000, but it's 3,999. And 3,999 is not just a nice number, it's a very nice number when it comes to subtracting or taking away 1,287. It's a very nice number. All these digits are greater than or equal to the digits underneath them. So 1 from 3 is 2, and of course you know that's 1,000 from 3,000 is 2,000. And 200 from 900 is 700, or 7. And 80 from 90 is 10, or 1. And 7 from 9 is 2. And so I have 2,712. I have to remember to put the 176 back in, so I've got to put these together. And so I can do this. This is 2,000, 100, and 700 is 800, so it's 2,800. The 7 and the 1 is a 8, and the 2 and the 6 is a 8. Oh, that's interesting. Since I just made these numbers, the difference apparently turns out to be, I say apparently, that's assuming I haven't made any calculation mistakes, is 2,888. That's the difference between 4,175 and 1,287. Again, the strategy I'm using is minuend splitting. So what strategy do we want to turn to next? Well, let me look at our list to make sure I'm not skipping over anything. So I've talked about the strategies of sequential counting, counting back, shifting, combination pairs, subitizing, compatible pairs, mental math, value expanded form, and place value expanded form, and minuend splitting. I want to turn to something called the hop, skip, and jump method, or the counting up method. So that's the next strategy, hop, skip, and jump. And we're going to talk about the strategy called hop, skip, and jump. And remember, in the session on the addition principle, we talked about, in fact, it was one of the last computational strategies we looked at, was the hop, skip, and jump strategy to facilitate addition. Now we're going to use the hop, skip, jump strategy to facilitate subtraction. The idea behind the hop, skip, and jump strategy goes back to the time before electronic cash registers, and it's how change was given out back in the 30s, 40s, 50s. And let's suppose that you gave someone $1 and you paid, let's say, 39 cents for it. So you have an object that you wish to purchase, and you have $1, and you want to pay 39 cents for this object. The question is, how much change do you get back? Well, you may not have cared, But the one behind the cash register that's not electronic and there's no colored buttons or no pictures on it, they have to give you the correct change back. And here's how they do it. It's a very clever way that they do it. They start out counting up to the dollar from the 39. So they go 39, okay? Then they give you a penny, 1 cent. That gets to 40 cents. Then they give you a dime, and that gets you up to 50 cents. And this is how the person operating the cash register is giving you change back. And then they'll go ahead and give you a $50. And some of you are now asking, what in the world is a $50? We don't have many of them floating around right now. So they give you a $50, and that way they've given you the change back, and they don't even really have to count out how much change they've given you back. They just know they've given you the right amount of money back. It turns out they're giving you 50 cents for the $50, a dime, that's 60 cents and 1 penny. So 61 cents is how much they gave you back in change. But the one who's giving you the change back doesn't care whether or not it's correct or not. They know it's correct by virtue of the strategy or the process by which they gave you back change. They essentially counted up from what we would eventually call the subtrahend. They counted up to the minuend, and that difference is how much is in change. Actually, this is like the strategy of shifting. We are moving up from the low number to the high number. So now let's put this together in a specific problem, this idea of hop, skipping, and jumping, and that's essentially what happened. I hopped 1 cent, I skipped 10 cents, and I skipped another 5 dimes or a half a dollar. Today you would probably go up to 75 cents with a quarter, and then up to another 25 cents. You'd hop up 25 cents to get to 75 cents and hop up another quarter to get to the dollar. But the change will still be the same. So let's put this together in a picture again. What are we looking at? We're looking at the hop, skip, and jump strategy. I had a student maybe 3 years ago, and when we were looking at the hop, skip, and jump strategy for larger numbers, and he said, George, what are we going to do when we have to start taking increments that are much bigger than hundreds? And I said, I don't know what you think is a good term. And he said, well, how about leaping? Okay, so here's the hop, skip, jump, and leap when he's going to go up by increments of 1,000. So hop, skip, jump, and leaping. He was the same student who came up with what I thought was a good phrase called backup plans when we're doing our multiplication. So let's take a problem. And let's take 327. Let's subtract 148. And I want to find out what that difference is. So my minuend is 327. My subtrahend is 148. And what I want to do is I want to figure out the difference between 148 and 327. Again, if you wanted to, I could shift this problem up by adding 52 to the subtrahend and making it 200. Because if I add 52 to the 148, it gives me 200. And if I add 52 to this one, it's 379. And so subtracting 200 from 379 is an easy problem. It's 179. But that's the shifting strategy. I want to talk about, and I've already talked about the minuend splitting strategy. I could use the minuend splitting strategy here by taking the 327 and writing it how? As a 299 plus 28. Then subtract 148 from it. And it turns out that subtracting 148 from 299 is a pretty reasonable calculation, and then add the 28 back in. So subtracting 148 from 327, I could do that by using the shifting strategy. I could do it by using the menu in splitting strategy, but I want to use the hop, skip, and jump leap strategy. So here's how we do this. When we use hop, skip, and jump in addition, we started with what kindergarten first graders are coached to start with, which is the larger number. So if this were an addition problem, I would be starting with 327 and figuring out what it takes to get to, if I was adding the 148, what would I get if I added 148 to 327? But this is a subtraction problem. And for the subtraction problem, just like I did in the illustration to show the counting up strategy, I started with a 39 cents, which is the subtrahend, and figured out what it took for me to get back up to the dollar, to find the right change or to find the right difference. The same is true here. So I'm going to start not with the menu in, I'm going to start with the subtrahend. So I'm going to start with the 148. And down here at the other end is 327. And I want to figure out how far apart are 148 and 327. What's the difference? So again, the way we accomplish this is depends on how comfortable the kids are with their arithmetic. And some of them will go in skipping and jumping without ever doing any hopping. You know, they'll pretty go 148 all the way up to maybe 200 something, like maybe 248 by jumping 200. But some kids will do this. They'll say, well, let's see, I'm going to do the following. I'm going to hop up just 2 units, and that gets me to 150. And then I like 100, and I know all I have to do is skip up 5 tens or 50 to get from 150 to 200. I said 100, meant to say 200. So I added 50 to the 150 to skip up to 200. And I'm looking down the road at where I'm heading. I'm heading to the 327. So why don't I go all the way up here to 300? Because I know to get from 200 to 300, all I need to do is jump 100. Okay, so I hopped 2 units. I skipped 5 tens or 50, and I jumped 100 to get from 200 to 300. And now all that's left is, how far is it to get from 300 to 327? Well, I can push those together. I can make that 27 added to 300 will get me to the 327. Now, what I figured out is what's the difference between 148 and 327. I did it by finding out these increments of 2, 50, 127. And so if I put those together, they'll tell me the total distance or the total difference between 148, 327. And the total difference is, let's see, I've got to put 100 together with 50, and then I've got to put it together with 27, and then I've got to put it together with 2, and that looks like 179. So 179 is the difference between 327 and 148. Looking back up here on our screen, notice in this strategy where I shifted by adding 52 to both the menu in and the subtrahend, notice that 379 minus 200 really is 179, and that's what we got down here. We got 179 by using the hop, skip, jump strategy. Let's do another one. Hop, skipping, and jumping. And so the idea is to take the difference and start with the smaller number. In addition, we start with the larger number. But in subtraction, we start with the smaller number because I want to see what's the difference between that small number, the subtrahend, and the larger minuend. So let's take, 1,247. Let's subtract 879. And I want to know what the difference is. Again, if I were doing this problem, I would probably take 21 and add it to this to make it 900. And I could find that difference pretty easily after I've added 21 to this. Or I could add 121 and make this 1,000. So if I weren't one to use shifting, I can change that into a nice, easy arithmetic problem. Or I could use minuend splitting and split the 1,247 up into 999 plus 48. And I can subtract 879 from the 999. That's an easy fix to modifying this problem to make it easier. But we're working on hopping, skipping, jumping, and possibly leaping. Okay, so we're looking at hopping, skipping, jumping, and possibly leaping. So once again, I'm starting with which number? Not the large one. I'm starting with the subtrahend. So I'm going to start down here with 879, and I want to see how many hops, skips, jumps, and possible leaps it takes to get down to 1,247. Once again, how I accomplish this is an individual matter. Kids will choose, for example, to be one kid who will say, I'm just going to take a little bitty baby step and I'm going to go up to 880 by just hopping one. And then I'll go from 880 to 900 by skipping 20. And then you'll find those that will say, oh, if I add 21 to this, I can see I can quickly get to 900. And then I'm trying to get all the way down to 1,247, so why don't I go all the way down to 1,200? And how many hundreds does it take to get from 900 to 1,200? Well, it's what? 300? And then finally, I can go from 1,200 to 1,247 pretty easily with a combination of hopping and skipping, 47. So now all I have to do is put these increments back together to find out the total distance between 879 and 1,247. So I have 300. I have 47. I have 21. I can add. So I get 300. I get 60. And then I get 8. So 368 is the difference between the two numbers that were given. And this strategy, hop, skip, jumping, and leaping, actually is a very well used computational strategy for subtraction here in East Tennessee. Why that is, I'm not sure, but kids enjoy doing this kind of thing. It makes sense to them. But there will be those kids that it doesn't make sense, and minuend splitting will be their choice, or shifting might be their choice. But this one works very well. Hopping, skipping, jumping, and possibly leaping. I don't know what would happen if we started moving in increments of 10,000. So let me see what's the next strategy that we want to look at. So I'll go to my list. So we've gotten down to minuend splitting. We talked about hopping, skipping, and jumping, counting up. And I want to talk about what's called Lexi's method. And it's because there was a student a year or two ago named Lexi who said, well, here's what I've been doing for several years for subtraction. And so she shared that with the class, and I looked at it and I said, that's kind of an interesting strategy. What it is a slight modification of the hopping, skipping, and jumping. So let me illustrate Lexi's method for finding the difference of two numbers. Lexi's method. And here's Lexi's method. Again, it's really taking the hopping, skipping, and jumping method and making a really good choice about that first jump or that first skip or that first hop. So here's the idea. Let me pick some small numbers to illustrate it from the very beginning. So let's take 93. Let me subtract 38 from it. And I want to find out what that difference is. So if I have a box of 93 cookies and I share 38 of those cookies with my calculus class, how many cookies do I have left in the box, to see if there's enough that I want to share with my 2 sections of class that I teach for aspiring young elementary teachers. So I've got 93 cookies. I'm going to subtract 38 cookies. I want to know how many I've got left. Again, shifting is a good strategy. Menuing, splitting is a good strategy. Hop, skipping, and jumping is a good strategy. But we want to talk about Lexi's method. Again, we're going to go back to the number line. And as we did before when we were getting ready to hop, skip, and jump, I'm going to put the small number, the subtrahend, down there at the left-hand end. And I'm going to put the larger number, the menuend, out here at the right-hand end. So I want to find the difference between 38 and 93. And here's what Lexi suggested that we might do. First find a number, a friendly number, that's close to the subtrahend. So in this case, I'm looking at 38. It could be 50, but 40 is even closer. So what I'm going to do is I'm going to take the 40. And so what I want to do is I want to find the difference between the 38 and the 93. Well, here's what Lexi discovered. If you picked a number close to 38, this difference she could calculate in her head. It's how much? 2. And this difference from 40 to 93, she wants to find 93 minus 40. But Lexi discovered if I pick a number close to 38 and I pick out this one, that friendly number is easy to subtract from 93. And then all I have to do is add that 2 back in. So she said, well, I'm going to take the 40 from the 93, and that one's pretty easy. Does everybody see that that difference is 53? And so she actually went and skipped from 40 to 93, 53 to get up there, but that calculation is easy. And then she adds the 2 back in, and so the difference is 55. So it's very much like hopping, skipping, and jumping, except instead of counting the way we were suggesting that you might count in the hop, skip, and jump strategy, she just does one little bitty baby step and then makes a gigantic skip or jump or leap up to the higher number. And she realized that when she does this, that friendly number is easy to subtract from the menuend. And as soon as she finds the 53, she adds the 2 back in, and so the difference is 55. So let's look at another example to make sure that we are clear on this one. And again, we are not trying to we're not trying to memorize strategies or processes or procedures. We're trying to look at ways that we might look at a problem where the underlying principle is, how do I modify this problem? What can I add, subtract, move, change, so as to take advantage of single-digit arithmetic, friendly numbers, or power 10 arithmetic. And this one is really taking advantage of, well, first of all, in this difference, it's easy. Here's a power 10 number I'm subtracting from 93. That's an easy problem. Let me go to a different problem. Let's take 146. Let's subtract, 108. Okay, I'm going to subtract 108, and I want to know what that difference is. 146 minus 108. Now again, we could do this problem with shifting. We could do this problem with menuend splitting. We could do this problem with hop, skip, and jumping. But we will want to use Lexi's method. So if I put this on a number line, the number I want to put this in is which number? the smaller number, the subtrahend. So I'm going to put the 108 down here. And I want to put the minuend, the bigger number, down here at this end. And for hopping, skipping, and jumping, I would want to find out, how far or how many hops and skips and jumps does it take for me to get from 108 all the way up to 146, because that tells me the difference between these two numbers. So what I'm going to do is I'm going to do what Alexi was doing, which is to choose a number real close down here, and it might be that all I want to do is pick 110 because it's very close to 108, and I know to get from 108 to 110 is only a pop of 2, and then I know this difference right here is 146 minus 110. Now, what is it you notice about 146 minus 110? All the digits in the subtrahend are smaller than or equal to all the digits in the minuend, so the subtraction is easy. 1 from 1 is 0, 1 from 4 is 3, and 0 from 6 is 6. And so the difference is 36. So 36 is how far apart I'm looking at these numbers, and 36 can't be the answer. So let's go back and see what it is that I've done. I put 108 down at this end. I put 146 down at this end. Okay. And so I hopped up just 2 units to get to a friendly number, 110. And now I want to find the difference between the 110 and the 146. Oh, I just found this difference, 36. I forgot to take the 2 and put it back with the 36. So this should be 36 plus the 2, which is 38. And it's good that I, thought that 36 was going to be the difference. I just went back and retraced my steps to make sure, if I understand this process, what is it that I found? Well, in this first part, I just found the difference to be 36, but that was just this difference here from 110 to 146. I still got to put the 2 back in, so it's 138. That's Lexi's method. Works for bigger numbers, but Lexi's method works better for 2- and 3-digit numbers. It is a bit of a struggle, how you work it when you work with 4- and 5-digit numbers, but it works very well with 2- and 3-digit numbers. But again, it's a slight modification of the hop, skip, and jump method. And I think there's one more, which is the 9's complement. So let me go back and make sure that that's the case. Yeah, I've talked about Lexi's method. One more is the 9's complement. Let's see what the 9's complement method is all about. So let me pause for a minute and think about the 9's complement, and then we'll start on the 9's complement.